Hello everyone, welcome to the channel of Algocamp. So now on this particular channel, we are actually releasing a series on data structures and algorithms where we are going to talk about some of the most important data structures and algorithmic topics which are extremely important for your upcoming software engineering interviews. Apart from that, these are some of the I would say topics that are very helpful in your day-to-day engineering job as well. We have already released a couple of series around searching, right? And we got a really good response on that. And from here, we are going to put really some awesome content around DSA. In most of these lectures, we will try to ensure that we focus on the intuition building aspect of the things, that how you are able to think about something, what are some of the things that people actually neglect but are going to clear some of the really important fundamentals. We are going to see coding implementation, but trust me, my focus is not going to be on the language delivery aspect of the things, that okay, you have to code this in C++ or Java. A lot of problems we have coded in multiple languages. Maybe some of the problems will be in C++, some will be only in JavaScript. I believe if you are somebody who is preparing for an interview, language in 2025 should not be a constraint, because most of the people can actually use ChatGPT to do language conversions. So my motive here is to make sure that you understand the concept in depth. You actually see how exactly somebody might have thought about the problem when they were carving out the problem, what can be some initial thought process, how you can actually drive yourself towards the solution. I believe these are going to be some really important videos that will be really helpful for your upcoming career. So do let us know what is your feedback. We are going to release a lot of more topics. Do let us know what all topics you want to have first, right? And the feedback is going to be important. Also, in case you are actually thinking to level up, you want to learn things with respect to low-level design, high-level design, overall system design for interviews, or you are somebody who wants to do project development in Spring Boot, you want to learn advanced Spring Boot concepts, or let's say advanced Node.js concepts, then we have a lot of courses, live courses running on algocamp.io. So you can check out the website courses.algocamp.io/learn, and there are a lot of courses that are actually listed. A lot of great discounts are actually going on all the courses as well. Do check them out. For each and every single course, we are going to add you to a dedicated Discord community where you can get your doubts resolved as well. All of the courses, we have made sure that we talk about things from the very beginner to the very advanced level that is going to help you level up in your career as a software engineer. So that being said, let's start the video without any further delay. So this is a new problem coming in front of you guys. This problem is from HackerRank. The power sum, okay, marked as medium, right? Let's see what the problem has to offer. The problem says that find the number of ways that a given integer x can be expressed as the sum of the nth powers of unique natural numbers. So in how many ways you can express x as the sum of nth power of natural numbers? For example, if x is 13 and n is 2, so you will be given x and n. Then you can say that we have to find all combination of unique squares, because n is 2, right? So the nth power is technically power 2, and power 2 is called as a square, right? So combination of unique squares adding up to 13. The only solution is 2 square plus 3 square, right? So if you will try to do square, or let's say nth power where n is equals to 2 of natural numbers, and try to make up some combination which sums up to x, then you will be able to find only one combination, that is 2 square plus 3 square, right? So that is the problem in front of you. If you see, the input format is you will just be given a value x and a value n. So you have to take two values as input, okay? And you can see, if you have to generate something like 10, so the only combination available is 1 square plus 3 square, because the value of n is 2. If n is 2 and x is 100, then there are three combinations. What are the three combinations? One combination is just 10 square, because 10 raised to the power 2 is also 100. Other combination is 6 square plus 8 square. Another combination is 1 square plus 3 square plus 4 square plus 5 square plus 7 square. Right. So there are So before we start this particular video, I wanted to actually talk about a very small thing. So this video is going to actually help you understand a real system design interview scenario. We are going to try to mimic a 45 to 60 minute kind of like a round where we are going to solve a problem very similar to how you will solve a similar system design problem in this short time frame. Now, of course, when you work as a software engineer in a company, you have relatively larger amount of time and you can do a lot of more deep dives in even very small level features. But in an interview, the temperament is different, the approach is different, and a similar scenario is actually explained in this particular video. So do consume the content based on that. Also, if you want to see more deep dives and want to understand these topics in a much more deeper level concepts, then do check out the link in the description section below for our System Design 2.0 cohort, where we have talked about a lot more concepts in a lot more detail, which will make you definitely a better software engineer. So let's just start the video. Three combinations. So here the answer is going to be 3. Whereas if you update n to 3, if the input is x is equals to 100, n is equals to 3, then the answer is just 1. Because then in that case, 1 cube plus 2 cube plus 3 cube plus 4 cube is equals to 100. No other cubic sum of natural numbers is going to give you the sum as 100. So this is the problem statement in front of you. And we have to figure out the total count. How can we do it? So how can we solve this question, right? So this is one of the most interesting questions that I have solved around recursion. And to be very honest, whatever knowledge we are having till now on recursion is appropriate and enough to solve this particular question. So let's try to like decipher things a bit. So you will be given a value x and you will be given a value n, right? And what you have to do nth power of natural numbers. You have to do nth power of the natural numbers, based on which you are going to check whether the sum of the nth power of natural numbers is somewhere around x or not. Now you know natural number starts like this: 1, 2, 3, 4, so on and so forth, right? These are natural numbers, right? Everything around this is only the corresponding natural number. So what I can directly say is that let me write it like this: the natural numbers that can sum up to x will be in the range 1 to x. Can I say that? All the natural numbers that are going to sum up to x will be somewhere in the range 1 to x only, no? You cannot take a natural number greater than x, raise it to some power of n and then expect the sum to be x, right? For example, if x is 10, definitely I cannot consider something like 12. Any power of 12 is never going to make the sum as 10, right? So if you carefully see, n is at least 2, right? N is never going to be 0, right? So 12 square is never going to do anything good for this value x. Can I say that? And technically, you can even reduce this space. You don't need to go from 1 to x. Technically, if I say that n is always going to be at least 2 and less than equal to 10, I guess. Let me just check the range again. Yes, less than equal to 10. Then I can say that 1 to square root of x will be the range of the numbers who can sum up to x, right? Who can sum up to x. Because even if for the smallest value of n, you can get square root of x. So let's say if x is 100, then I cannot take anything beyond 10. I cannot take anything beyond 10 so that some power of that number is going to become x. For example, I cannot take anything like 12. 12 square is 144. I can never make it as x. So the last number that you can take for some power of x is going to be square root of x. And if the value of n increases, it will be even less than square root of x. That is the part. But still, for our cases, let's keep square root of x as the total bound that we have to keep. So what I'm going to say is that from 1 to square root of x, I have to find how many combinations of numbers we can have such that sum of nth powers of that number is equal to x, right? So let's say we have 100. So for 100 the range becomes 1 to root of 100, that is 1 to 10. So from the range 1 to 10 I have to get some combination of numbers that can sum up to 100 considering n is equals to 2. So what I can say is that I don't know how many combinations are there, right? But let's say if I somehow try to form different type of subsequences from this range 1 comma 10, so there will be a lot of subsequences, right? 1 1 2 1 3 1 4 and so on. Maybe something using that we can do, because if you carefully see the answers, here 10 is just one valid subsequence. 6 comma 8, because 6 square plus 8 square, so if you say 6 comma 8 is a subsequence, then this is a valid subsequence. 1 3 4 5 7, this is a valid subsequence. So if somehow we can reduce it on the subsequence logic, then maybe we can do something. So what will I say is that I want to generate the sum x with the powers of n, right? So let's say I want to generate the sum 100 with the powers of 2. So what I can say is that let's say we start with 1, and for 1 maybe we can have two choices. Maybe I can include 1 in my answer or I can exclude 1 in my answer. If I include 1 in my answer, then I need to go for creating a sum 99 with the power of 2 from 2 to 10. Why? Because 1 square I have considered as 100 inside 100. If I do not consider it, then this will remain as it is, 100 will remain as it is, right? Then again for 2 also we will be having two choices. For 2 also you'll be having two choices. If you consider 2 or you don't consider 2. If you consider 2, then you will be left with 95 comma 2 comma 3. If you don't consider it, then 99 comma 2 comma 3. Here if you considered 2, then 96 comma 2 comma 3, and if you don't consider it, 100 comma 2 comma 3, right? So what I'm trying to say is, let's try to formulate all possible subsequences. Let's try to formulate all possible subsequences. For every subsequence we have a choice, right? That in the given set of element is 1 to square root of x. In the given set of elements I can choose an element or I can avoid an element. Whatever element you choose, you are going to take its contribution in the sum, right? So if your sum is going to be expected as x is equals to 100 and you chose 1, then inside your sum you already have the component of 1, that is 1 square. So now you just need to create 99. If let's say you chose 2 also, then you will also consider the component of 2 square, that is 4. So now you just need to make 95 from 3 to 10. Can I say that? Can I say that? Can we not just think about it in these terms? That is, try to reduce the problem such that it becomes similar to subsequences. It becomes similar to subsequences. It becomes similar to subsequences, right? So let's take an example. Let's take an example like, let's say, let's take a small example. For example, 10 comma 2. Let's take 10 comma 2. Okay. So for 10 comma 2, what is the square root of 10? Approximately somewhere around 3, right? So the set is going to be 1, 2, 3, right? Let's see. So we'll start with 1. I have two choices. I can either include 1 or exclude 1. If I included 1, then total sum is expected to be 10. I am including 1 square. So I'm left with 9 comma 2 comma 2. If I don't include it, then I'm left with this. Okay. Now, if I include 2, not include 2, include 2, not include 2. If I included 2, then I'm going to take the contribution of 2 square in x, which is just left with 9. So 2 square is 5. We are left with 4 comma 2 comma 3. If you don't consider anything, then we are left with 9 comma 2 comma 3. Here if you consider 2, where the sum you want to create is x, so 2 square is 4, you are left with 6 2 comma 3, otherwise 10 comma 2 comma 3. Now again, two choices everywhere. Include 3, exclude 3. Now, can you include 3 here? 3 square is 9. The sum you wanted to create is 4. You cannot do this. This call is not possible. And if you don't include 3, you are left with 4 comma 2 comma 4. Right? This is what a base case, because the only set that you can go from is 1 to 3. This became 4. So technically both of these paths are never going to give you answer. So this is also invalidated. Right? Okay, cool. And technically this should be 5. This should be 5. This should be 5, but still this is invalidated. Now 9 comma 2 comma 3. If you include 3, then you need to take a contribution of 3 square. What is 3 square? 9. What is the contribution of 9 inside 9? The whole contribution, right? So you are left with 0, 2 comma 4. The moment your x becomes 0, you have found one possible way. So I can keep a global answer, which was initially 0. I'll set it as 1 inside my base case. So one possible answer was 1, don't take 2, and then take 3. So 1 square and 3 square is one possible answer. Right? Okay. Then here 9 comma 2 comma 4, this is not going to give you answer because you have surpassed the square root of x. Here 3 into 3 is 9, greater than 6. You don't need to make this call. And then 6 comma 2 comma 4 also is going to do nothing. 3 square is 9. So you are left with 1 comma 2 comma 4. And now you cannot do forward because you are out of the, I would say, set limit. And this 10 comma 2 comma 4, this is also out of the set limit. So only case where you actually got x as 0 was this. So what I'm trying to say is that I know that my set of numbers from which I'm going to get some combination is 1 to square root of x. So for every number in this set, I will give them two choices, that I want to include that number or I don't want to include that number. If I'm going to include that particular number num, then I'm going to raise it to the power n. If I don't include it, I avoid it. If I've included it, then I'm going to reduce it from the sum x, because eventually its contribution is going to be taken inside x, and that's it, right? So if I write a recursive function f that takes a value x, that takes a value n, and let's say that takes a value I, okay, it takes a value, corresponding value I. So what I can say is that I have two choices. Either I will include the power of I raised to, either I will include I raised to the power n, or I will not include it. So I will say f of x comma n comma, or I would say, if I include it, then this will be x minus I raised to the power n comma I plus 1. If I don't include it, then it will be just I plus 1, right? So we will assume that the function works correctly for these two cases. We will one by one call them and we will get the answer for this. Here I've included I raised to the power n, so I will subtract it. Here I have not included I raised power n, so I'll not subtract it. At any point of time, if x becomes 0, then I will do count plus plus, because I found one possible answer. If I raised to the power n is greater than x, then you don't even need to make any calls. Yeah, you don't need to make any calls, right? So handling cases like these we can do. And at any point of time, if I becomes, or I should say I into I becomes greater than x, then also I don't need to make any call. So a few base cases we can write that can simply help us to solve the problem. So we'll say this function is going to give us the total number of combinations such that we have summed up nth power of natural number to make x. So this is going to give us total combinations. And if somebody asks you to print the combination, for example, at some point of time, instead of counting, somebody asks you to print the combination, then you can just keep an output variable. If I'm going to include I raised to the power n, I will reduce it here, go to I plus 1, and inside my output, I will append I raised to the power n. If I'm not including it, then I will not append anything. That's it. Similar thing we did in subsequences, right? That if I am going to pick an element, I add it in my output. If I don't pick an element, I don't add it in my output. And this time the element that is we are picking is I raised to the power n. Now you might be thinking how we can calculate I raised to the power n. So either you can use our own a power function, or we have a power function inside C++ that can give us I raised to the power n very easily, right? So this will be a simple logic to solve this problem, right? So let's try to write the code. Let's try to write the code for this. Then we will be able to get a better perspective on this particular problem statement. So if you want to code it, let me make it to the parallel layout. Okay. So they have already given us a bit of template. I don't want to hamper with their template. They're asking us to just implement the power sum function. Okay. So above it, I'm going to write a function. Let's say void f. It is going to take a parameter x. It is going to take a parameter n, and it is going to take a parameter I. I'm going to keep a global variable because the count I'm going to increment in the base case. So I'll say int result is equals to 0. Okay. And then I'll make two calls. So first of all, I'll say int p is equals to int of, there's a power function. Okay. That will help us to take I raised to the power n. Okay. And we need to typecast this power function because it returns double in C++. Then I'll say f of x minus p comma n comma I plus 1 and f of x comma n comma I plus 1. What is x minus p? P is I raised to the power n. I raised to the power n. Okay. These are going to be the two calls. Let's try to figure out the base cases. One base case can be if at any point of time, if I into I becomes greater than n, then we are out of our given set, right? Because I square greater than n is I greater than square root of n. Sorry, this should be x. I greater than square root of x. And we cannot go beyond square root of x. So I'll say return. Okay. Then if at any point of time x becomes 0, you have found one valid answer, you will say result plus plus and you will return. So we found one valid answer. Okay. One more case that we can write is that if p that you are going to eventually, or let's do it like this. If x becomes less than 0, then also you cannot do anything, you return, because you are doing x minus p, right? So for example, if the power was greater than x, then it will technically go less than 0, right? So you don't want to do that, and you are going to return it from here. And from my power sum, I'll first of all call x comma n comma 1, and then I'll return result. Okay, this is my global variable result in which I have the final set of answers. Let's try to run the code. I'm not hampering any other piece of code that I have given to us. Let's wait for a while. So actually HackerRank is on scheduled maintenance. So I'll separately submit the code, right? So for that time being, let's do one thing. Let's create a new file here. Power sum. Okay. Paste the code implementation that we have done. I'll just avoid anything extra that is there. And I don't need all of the header files. Cool. Let's try and test it here only. Okay. So we'll say int x, int n, c stdc in x n. Then we will call cout power sum x comma n. Cool. And we need the math library, so hash include math.h. Okay, this should be a good to go. Let's try to run the code. Let's see. Okay, 1 second. Let me try it on terminal. So PSA. Okay, so here we have power sum. So let's compile it. Minus overrun /run. Okay, so it's expecting an input. I'll say x as 10, n as 2. Okay, it's giving us 0. 0 should not be the answer. Let's see what is going wrong with the code. Okay. Okay, so let's see. Let's try to debug our code a bit. Okay. So for the timing, I'm saying let's say x is equals to 10, n is equals to 2. Let's put a debugger here. And then let's see. Okay, so if we first of all calculate power of I raised to the power n, 1 raised to the power n is just 1 only. No problem, no problem. And I'm going to make a call x minus 1. Okay, this is not going to technically give us any answer if I remember my recursion tree. Right, I'm going to make this call. Okay, so power becomes 4. So 2 into 2 greater than x. No problem. No problem at all. And if I see, if I watch on result is still 0. Interesting. Let's try to debug what happened. So I guess the issue is I need to put the positive base case above, because if you carefully see here 4 square will become 16, which is greater than 10, right? So I was initially returning it immediately. I don't need to do that. Okay, now I believe things will work fine. I can remove this log, and let's do one thing, avoid the hard code also. I hard coded it for the bit of debugging. Let's compile. So 10, 2. Okay, the answer is 1. Makes sense. 100, 2. The answer is 3. Very good. 10, 3. The answer is 0. Makes sense. No. So no cube is actually going to give you the value 10. But if you do 100, sorry, my bad. If you do 100, 3, then the answer should be 1. So we are technically getting the right answers, right? And if in case you also want to print the answers, then you can put a string output here, right? Cool. Now one very small optimization that we can do is, here I'm doing I into I greater than x, considering that our reversed bound is square root of x. But I know n can be more than 2, it can be 3. So we need a bound cube root of x or something like that. So instead of doing I into I greater than x, I have already calculated I raised to the power n, right? I can just say if p is greater than x. If the power that we have becomes greater than x, I don't need to do anything. So if I compile again, 102 gives you 3, 10, 2 gives you 1, 103 gives you 1, 10, 3 gives you 0. So all the cases are working, and this should be a good to go implementation. You can try to submit it on HackerRank once it is up, right? It's under maintenance while we are having this session. So you can try to separately submit it on HackerRank, but I believe this overall problem is making sense to everyone. I'll just add the problem link here.